Hi, I'm Jonathan Aldrich. Let's talk about recursive types. A recursive type is one whose objects may contain one or more references to other objects of the same type. Recursive types support common heap data structures such as lists or trees. For example, if we have a list, then we have the first link in the list has an element and then a pointer to the next link in the list, which is also a link, right? So it's recursive. One link refers to the next one. Similarly, in trees, each node in the tree refers to its children, which are also nodes in the tree. Recursive types, in practice, are usually combined with a record and maybe a union type. The idea is that a recursive type typically needs to hold something in addition to the recursive reference. And generally, there needs to be a non-recursive variant of the type as the base case for recursion. Thus, we have a union as well. For example, classes are unions, records, and recursive types all put together. ML data types are unions and recursive types. They don't have records, but usually a record is inside the ML data type, or perhaps something like a tuple. Languages with null can include simple unions by simply using a null pointer or a reference for the base case in recursion. So, for example, at a tree, the leaves of the tree would have null as their children, and the end of a list would have null. And so a list type then doesn't have to be explicitly a union because there's sort of an implicit union due to null being a case of every type. If we look at a recursive tree data structure in a language with pointers, it will be structured like as the following shows. So on the right, we have an abstract conceptual tree, right? So we have at the root, we have children x and y has children z and w. Now, when we represent this with recursive types, each node in the data structure will refer to right and left nodes of the same type. So here, when we would concretely represent this with a node that has three fields, we have R for the contents, and then the left field goes down to X, the right field goes down, points to Y, and then X has two fields, stores the value X, and then left and right pointers of null. Y has pointers to its children, and so on. And so there's a correspondence between the data structure and the abstract tree. Lisp is kind of an interesting example because pointers are implicit in Lisp. It uses a reference model of variables. And recursive data structures are typically just built out of con cells, right? Con cells are the primitive, so everything is a list. But then how do we form trees out of lists? Well, it's not too hard to do so. Basically, we have in Lisp con cells and atoms. And so each cell is either tagged with a C or an A to denote whether it is a con cell or an atom that represents just a primitive type of some kind. So how do we represent a tree? Well, a tree node will be a list of length 3. It'll be 3 con cells, and then it will end. The first con cell, its contents will be the actual node in the tree, right? So in this case, it'll be an atom holding the value R, because R was at the root of our tree. Then the second element of the list, its contents, will be a pointer down to the left subtree. And then the third con cell, its contents will be a pointer down to the right subtree, right? So each node is a little linked list, and the contents of the second and third elements of that list will point down to the children. And then the children are structured in a similar way. How can we describe recursive data types in OCaml? Well, here's an integer list type in OCaml. We have type int list, and it's a union type with cons and nil. And then the cons has a value, right? That's a linked list cell, so it has a value. And then it has a next, which is an int list. And so here we can see why the type is recursive, right? We're using the int list type in the definition of int list. Here, the vertical bar denotes a union type, and the brackets denote a record type. As I mentioned earlier, these are often combined with recursive types. How do we model recursive types formally? Well, to understand them better, let's identify their essence separately from records and unions. What we're going to do is add a recursive type, rect.tau, to our grammar. So in this construct, rec means recursive, t means the name of the recursive type, so int list in this example. Tau is the type's definition, right? So that would be the union and record that holds the information inside the int list. And the whole idea is that the name t can appear in the type tau on the right. So formally, our grammar for tau has all the things it had before, primitive types, functions, who knows. right? And then we have the recursive type rect_t.tau, and then we can also use t now as a type, right? Because inside tau we have to be able to use t. So let's look at how we can model lists with this construct. So we have the top level type is a recursive list type. So we have rect list, and then the type on the right-hand side is, first of all, a union of cons and nil, right? Because a list can either have, at least one cell and then the rest of the list, or it can be empty, which would be nil. Nil just has a unit type. There's nothing to store there. Whereas cons is a record that has a value for the integer, which holding an integer, and the next field, which holds the list, right? So again, that's a use of the recursive type. We're using type list within the definition of itself. Now, conceptually, a recursive type is equivalent to its definition, okay, on the right-hand side. And so we can illustrate this or witness this equivalence by unfolding a recursive type, basically replacing the type name with its definition on the right-hand side. So if we take a type rect_t.tau and we unfold it, what that means is taking all the t's that are in tau and substituting them with the whole recursive type rect_t.tau. Okay, so the notation here just does that substitution, right? It says substitute t with rect_t.tau everywhere in tau it occurs. Here's an example of this happening, right? So let's look at our recursive type from before, okay? Remember, we start with the declaration rect list, and then we can use list in the next field of our list cell example. So if we unfold this once, then we'll get just the right-hand side, right? So we start with union. It's a union between cons and nil. We have the record inside the cons. But in the next field, instead of just having list, now that wouldn't make any sense because there's no rec outside, right? What does list mean? So we have to paste in the whole definition of list right there, right? So we have rec list.union, cons, nil, etc. And then list is inside that bound part of the recursive type. We can then unfold again, right? We can unfold the inner thing, and we get, continued unfoldings of this union with the cons cell, with the record, and then another recursive type. There's a symmetric fold operation that goes from the big type with list expanded down to the type with the recursive type itself. Now, this folding and unfolding is basically the equivalence between the integer list type and its definition. But how do we know when we write a compiler, when we write a type checker, how do we know when to fold and unfold, right? To reason about this equivalence. How does it actually work? Well, conceptually, we could just unfold as many times as we want, but it's not practical because the fully unfolded type would be infinite, and we can't represent an infinite type explicitly. So what type checkers do in practice is they unfold just whenever they need to. But they need hints about where to unfold, right? And so if we actually had a recursive type all by itself, we would have to sort of put in those folds and unfolds as hints. That's what our formal language is going to do. But a practical language, that would be a little bit annoying, right? So practical languages don't provide recursive types by themselves. They combine them at least with unions and often with fields as well. So ML data types, C structs, Java classes, we all see these done in this way. And then operations on the combined type, right? The data type, the struct, the class, they trigger folds and unfolds of the recursive type. So whenever we create a class, whenever we create an instance of a struct or a data type, then we do a fold operation to wrap up that data structure into something of the type, class T. And then an unfold operation happens whenever we go inside, right? So if we're pattern matching over an ML data type, then we'll unfold it so we can see what's inside that data type and match the patterns properly, right? Or if we access a field in C or Java, then we'll look inside the recursive type, we'll unfold it, we'll see what fields are there, and then we'll get the field that we want. Let's look at handling this formally, okay? So we'll extend our type syntax with recursive types, as I showed you before. We'll extend our expression syntax with folds and unfolds. Remember, these are not going to be in a practical language, but in our formal modeling, this enables us to know when we have to go inside a type and look at the contents, or when we fold it up. And then we have folded values, right? So our fold operation basically keeps track of the folded recursive type, and it lets us know when we have a recursive type as opposed to, some type that's just, a given set of fields and things. So let's look at our semantics now. So folded data structures are going to be values. And so we only need to add a rule for unfolding those values to get at their contents. And so if we have an expression unfold of E, then E had better evaluate to some fold expression, and then unfold of E gives us the value that was inside the folded thing. The typing rules will convert between folded and unfolded representation of types, right? So if we have an unfold E expression, then we expect E to have some recursive type, and the unfold expression will have the right-hand side of the recursive type with the recursive type substituted in for any occurrences of the recursively bound name. Similarly, fold will take something that is, just an ordinary type, but it happens to have a structure that allows it to be folded, and it will fold it up into a recursive type. Let's think about subtyping. So the main rule for subtyping between recursive types is basically just analogous to depth subtyping. So if we have two recursive types, one will be a subtype of another if the definitions on the right-hand side are in that same subtyping relationship, right? So that's what the premise of our S recursive rule says. Now, the one thing is, whenever we look at the relationship between the right-hand sides, right, tau and tau prime in this case, we might get to the recursive type, right? And at that point, we don't want to look inside again because we would never stop, right? We create like an infinite derivation of subtyping, but in fact, infinite derivations are not really a thing. That induction doesn't work like that. You have to come to a base case eventually. And so what we do is we say, okay, we're not going to substitute in the recursive type when we compare the contents on the right. We'll just leave the names in, but we'll keep track in our typing environment gamma of the fact that we're just going to assume that T is a subtype of T prime, okay? Now, that may not be true in general, but if our application of SREC works out, then it will be true. And so it's sound to sort of assume that when we're checking the right-hand side, because if the check fails, that's the only situation where it won't be true. So we technically need a second rule, which allows us to use this assumption that T is a subtype of T prime in gamma, when we're looking at the right-hand side to make sure that they're subtypes. Let's check our understanding of recursive types.